All right, welcome to the ML Scalability and Performance Reading Group. Today we're going to be covering Megatron-LM, training multi-billion parameter language models using model parallelism. And this is a very famous paper and I'm very excited to cover it for a while because it's so foundational in the sense that it essentially introduces the concept of tensor parallelism, and it also is used as a baseline in many of the other papers which we've covered so far. So this is an important one to know about. With that, we can go ahead and get started. So I'm not going to spend too much time on the abstract and introduction. Basically, in the abstract, I just briefly discussed that they're going to be introducing a type of intra-layer model parallelism. So this is in contrast to things like pipeline parallelism, which are an inter-layer form of model parallelism, where we are partitioning the model between layer boundaries, kind of horizontally, so to speak, and kind of grouping these layers into stages and so on, like we've talked about in prior sessions with like G-pipe, pipe dream, zero bubble pipeline parallelism. Whereas in this is like a different category of model parallelism where we're kind of partitioning the model vertically. And by that, what I mean is we're actually partitioning the actual tensors that are involved in computations and performing these computations in like a distributed fashion. And a lot of careful thought has to be put into this in order to avoid communication overhead from exploding. And we'll see how the authors do that. And you can see here they also point out that, with this new approach, they were able to scale from a single chip up to, well, they don't explicitly say this in the abstract, but they scale from single chip training to 512 chip training with 8-way model parallelism and maintain 76% scaling efficiency, which means that it's not perfectly, it doesn't scale perfectly linearly. There is some overhead that will, be a bottleneck as we continue to scale up. But at the time, this is published in 2020. This was pretty good. So yeah, in the introduction, then moving on, just give kind of a brief background of language models, how they're becoming bigger. These optimizer states can get really large with 2 parameters per or 2 bytes per parameter, right? We have like the first and second moment with the atom optimizer. And essentially the memory usage becomes quite large, and so they talk about several model parallelism approaches that attempt to overcome this. And they mentioned G-pipe, which we covered a previous session rather. But kind of the point they're making here is that these all require like custom frameworks or different compiler tricks or rewriting the model. And their claim here is that this is kind of a more generic approach that they're going to propose. Yeah, and then here's where they kind of go over the performance I talked about. They start with a 1.2 billion parameter model, a single V100, and measure 39 T-flops. And basically, they scale this up to 8.3 billion parameters on partitioned over 512 GPUs with 8-way model parallelism. And so they are achieving 15.1 petaflops, which if you multiply 39 T-flops times 512 GPUs, you get this number here, 15.1 petaflops, is 76% of 15 times 39 teraflops. So decent scalability, but as we now know in the future, tensor parallelism actually does have quite a bit of communication overhead, and it's typically kept in intranode setting for that reason, where network bandwidth and network bandwidth is higher, network latency is lower, so the communication bottleneck isn't as severe. But yeah, this is what they showed. Even with the 512 GPUs, they were able to maintain 76% scaling efficiency. So pretty cool. Let's see how they did it. I'm going to kind of skip past some of these sections of the paper because they're just kind of giving background on transformers, multi-head attention, the kind of memory usage that arrives, and some of the problems that need to be overcome there. They give a brief background on data and model parallelism. Whoops, I skipped ahead. Just to kind of set the stage for other methods and techniques in this space of trying to train larger models and partition the models in such a way that we can overcome the memory bottlenecks. And yeah, now finally they introduce the actual method that they are proposing here. And so this section is very important to go through line by line, because this is really the meat and potatoes of the whole paper, so to speak. So what I have here is I've got the paper with the key sections highlighted, and then I'm going to be referencing some diagrams I wrote along the way, because personally, some of these statements, they only kind of describe in like one very brief sentence, and it really requires some thinking and to understand, in my opinion, and perhaps even like drawing it out to like really make your understanding concrete, at least for me. So with that, we'll get started. They say a transformer layer consists of a self-attention block followed by a two-layer, multi-layer perceptron. Cool. We all know this. We introduce model parallelism of both these blocks separately. Okay, they start by detailing the MLP block. The first part of the block is a GEM, general matrix multiplication, followed by a Gelu nonlinearity. Cool. So we have inputs X, A our weight matrix, so we do XA, and then Gelu nonlinearity. That's the first layer in the MLP. So now one option they say to parallelize the gem is to split the weight matrix A along its rows and split input X along its columns, as they show here in this notation. So input X, they use this notation to show that it's split along the columns, and this notation to show A is split row-wise along the rows. And now what they say is, this might be like one obvious way to do it, but what they say is this partitioning will result in Y equals Gelu x1a1 plus x2a2. Since Gelu is a nonlinear function, Gelu of x1a1 plus x2a2, which is what we'll have, is not equal to basically applying the nonlinearity to each part of that sum separately, which would be Gelu x1a1 plus Gelu x2a2. And so this approach will require a synchronization point, basically inter-device communication, before the Gelu function. Okay, let's pause here. We can just take their word for this, but I think it's much more helpful to actually diagram this out and see why we need this synchronization point, see why this particular property does not hold for nonlinear functions as they state here. So let's go to this diagram. And so what we're looking at here is the first gem in the MLP. And this is the quote-unquote bad option, the one that they're saying, well, let's just see why it's the bad option. So here we have our inputs X split column-wise, as they stated, right? X1 and X2, so split column-wise. And we have our weights split row-wise, so A1 and A2 split row-wise. So now what you can see is basically in order to compute our output matrix, there's two ways we could do this. One is for every single output element in our output matrix, we would have to compute a dot product between a row of X and a column of A. But as you can see, due to the partitioning, to compute that dot product, we will have to cross device boundaries, right? So this row times this column, the dot product, you can see they're split across devices. So that would mean for every single output element, you have to do inter-device communication. So this is just wildly impractical, right? That's just like a non-starter. We can't have that much communication overhead. So what's another option? Okay, we could just keep computation local on the device for as long as possible. So and see how far we can get before we're forced to do synchronization. So X1 is on device 1, A1 is on device 1. So let's do that mapmul, right? X1 by A1. So the purple arrow here and the purple arrow here. If we do this mapmul with these two shapes, you see we'll get an output, X1A1, which has the number of rows in X1 by the number of columns in A1. So we get this. So it actually has our full output shape that we're expecting for this mapmul, but the individual elements in it only have partial results. Because as you can see, we didn't, to complete the full result of any element in X1A1, or in this output matrix rather, we would need to also include the rest of the dot product, which exists on X2 and A2. So X1, A1 is just a partial result, okay? Now on X2, A2, this is the other device, it will also compute its local mapmul, X2, A2. So the pink arrows now, right, this row right here, this column right here, and what we'll have is this other matrix here, X2, A2, which has the number of rows in X2 and the number of columns in A2. And so these are both the same shape, but each contain partial results. And so what we now need to do at some point is sum these together to complete our output matrix. We need to reduce the result, have a complete, accurate output of this matmul, because we need the numerics to be equivalent to the unsharded version of this matmul, right? Because the math can't change, just the when and how we do the computation can change. That's the only thing we can change. So otherwise our model just won't converge properly. So now the question is, when do we want to do that reduction? Well, ideally, what we would like is to avoid inter-device communication, avoid this reduction for as long as possible, right? But it turns out we would be forced to, if the partitioning is done this way, we are forced to do the synchronization immediately, right now, in the very first gem in the MLP, right? So this would be one all reduce already in the first layer of the MLP, and we still have more to go. So basically, why is this? So it's because of what they said about the nonlinearity not having this property where the GELU of, so basically if we did this, and let's just step back for a second. If we did this matmul in the unsharded form, we would take this output matrix in its complete form and apply the GELU. Okay, so our two options are either to apply the GELU with a sharded format. Our two options are to either apply the GELU to each of these individually, or to apply it to the summed result, right? So if we sum the result and then apply the GELU, and we all reduce and then a GELU, that will produce the correct result, right? That's this form right here. But GELU of x1a1 plus x2a2. Okay, but this sum, that's the problem. This sum requires the all reduce. So let's try the other option. What if we don't do the all reduce and we just apply the GELU to each matrix individually and then continue on through our forward pass? This is the problem. Applying the GELU to each of these is not numerically equivalent. It's not mathematically equivalent to applying the GELU to the sum. And you don't just have to take this as some axiomatic truth. We can look at a concrete example here. I made the example just using ReLU. It's a different nonlinear, of course, a very simple one, just because we can easily do the math on our heads here rather than this like more complicated one. So if we just look at the example with some just scalar values and make this simple, ReLU of -1 times 2 plus 1 times 1 would be equal to ReLU of -2 plus 1. And that, you sum them together, ReLU, it would be ReLU of just -1, and then ReLU of -1, as we know, is 0. Okay, but then what if we apply ReLU to the individual products before summing? That would be ReLU of -1 times 2 plus ReLU of 1 times 1. So then that would become ReLU of -2 plus ReLU of 1, and that would become 0 plus 1, and that would become 1. Okay. So as you can see, 0 does not equal 1, thus they are not mathematically equivalent. So this is kind of the key point that they are making here, is that this obvious form of sharding where we shard both the inputs and the weights will not work. Or rather, we would just be forced to do a all reduce very early on here. So now what they want to do, which we'll go back to the paper, they want to see, is there another option where we don't have to do this all reduce? So they say another option is to split A along its columns, A1 and A2. This partitioning allows the GELU nonlinearity to be independently applied to the output of each partitioned gem. And as you can see here, this is what they're stating. They're saying, partitioning A1 along the columns, the output should be equal to GELU of XA1 concatenated with GELU of XA2 column-wise, right? So this has the advantage as it removes a synchronization point. So let's see what that means and see why that actually works. So if we scroll down here, here's the good option that they're proposing here that removes this forced synchronization point. Here they actually have the full X. So in this case, they're not partitioning X column-wise. They have the full X replicated on each device. Okay, so that's one trade-off they're making. But now they partition the weights column-wise, as they said, right? Here, split A along its columns. And now we can do the full dot product, right? Of a full row of X and a full column of A, A1 in this case, and get a complete output element in the matrix, in the output matrix, right? That means that, we can do this mapmul X and A1, do all these dot products, and what we'll get is the first half of this output matrix on device 1, and that will have number of rows in X and the number of columns in A1, and we get this. Do the same thing with A2, and we get this. We get the other half of the matrix. And so now, since these are complete results, we can apply GELU to them independently. There's no sum that's still waiting to happen somewhere. This is the complete result, so we are safe to apply GELU. Okay? So that's the kind of key point that they are making here. So it removes that synchronization point. And yes, we can't partition this X, but the overhead of the extra synchronization that would have to occur in the first option is, it outweighs the, it's like it's a favorable trade-off, I guess is what I'm trying to say. So let's keep going. We partition the first gem in this column parallel fashion and split the second gem along its rows so it takes the output of the GELU layer directly without requiring any communication as shown in figure 3. So they have their figure 3 here. I don't think these diagrams are very great. That's why I made my own. But yeah, you can see X in their diagram is replicated. F is the identity operator in the forward pass, they say. F is the identity operator in the forward pass and all reduced in the backward pass. So X identity, so it's still X, full thing. It's like replicating it across the devices. Then, XA1, GELU, and we have our Y1 and Y2 just like we have here, right? This is a Y1 and Y2, and then this is going to go through. Well, okay, yeah, I'll show. We haven't got to that in my diagram, so let's break down the second gem that they just talked about first before we go through their diagram. So they say. They split the second gem, so they partition the first one in the column-wise parallel fashion like we did here. A is split column-wise. They split the second gem row-wise along its row, so it takes the output of the GELU layer directly. So B is the second matrix. We split it row-wise. So here we have our XA1 and XA2. Those are the outputs of the GELU. They're coming here and being our inputs to the second linear layer, right? So now, if we scroll over, XA1, XA2, you perform these mapmuls locally. These are both on device 1. And the bottom ones are both on device 2, and we get these outputs, right, O1 and O2, and because that's the number of rows in this XA1 and the number of columns in B1, so you get this square, and same thing with O2, same shape, and so now these are partial results that need to be all reduced, right? And so now you perform the all reduce, but the thing is we're at the very end of the layer. So we avoided having to do 2 all reduces. We got away with only having 1 at the very end. And now we have our full output complete result for the MLP, and we go through our dropout. Okay? So that's what they're saying here in their diagram, just to compare. They have their outputs of GELU, and then they do Y1 times the B1. It doesn't show the partitioning in these diagrams and why it works and why communication overhead is avoided. So I thought my diagrams would be helpful to understand that. But yeah, you can see now G is where we do all reduce. So G is the all reduce in the forward pass and identity in the backward pass. So G all reduce, then we go through dropout and we have our output of our MLP. Cool. So that's the MLP. Let's go on to self-attention. So self-attention, let's just read what they say. For the self-attention block, we exploit the inherent parallelism and multi-head attention operation, partitioning the gems associated with the key, query, and value in a column parallel fashion, such that the matrix multiply corresponding to each attention head is done locally on one GPU. Okay, so let's break this down. Scroll down, I have a diagram for this. Basically what they're saying is each attention head in multi-head self-attention can operate independently. The calculations that go on within one head of attention are completely self-contained. Thus, we can parallelize this, and it's very natural to parallelize this across GPUs. So, as you can see here, X again is replicated. We can see that in their diagram here. F, the identity operator on forward, all reduced in the backward. So on forward, X is replicated to both devices. Okay, now let's go back to my diagram. So X exists on all the devices. So X is our input activations for our self-attention layer. And now we need to do our projections, right? We need to project from the embedding dimension to the head dimension. And what is going to happen, so these are each one head, basically. Q1, WQ1 is associated with the first head, WQ2 is associated with the second head, and so on, with the K's and the V's. So as you can see, we go, compute our dot products here, and we'll end up with, Q1, our queries, and Q2, our second set of queries for the second head, and so on. Same thing for K, same thing for V. So now we have our full projections, Q, K, and V. And these are one head each. So, Q1, K1, V1 are one head on one device. And, oh, whoops, I forgot to update. I just noticed this. All right, we're doing some live editing here. Okay, yeah, so basically each device has Q, K, and V projections for one head. That's the output. Okay. Now if we move on, now we're going to use our Q, K, and V projections to compute our self-attention layer. So now we're going to do our, our traditional Q1 by K1 transpose, and we'll get our S1. This is just using vanilla self-attention in this paper. We're not doing any kind of flash attention or anything fancy. This paper predates those techniques. So now we have our raw attention scores. We go through softmax to get probabilities for row-wise. Then we apply, we do our map mul between our attention scores and our values to get like a weighted update of our original input tokens and embeddings. And basically, now they need to be projected back to the embedding dimension. This is the linear output layer, right, in our self-attention. So let's pause now and go back to the paper because we've talked about the self-attention. So we're now getting into the linear layer afterwards. So let's actually see what the paper says first. This allows us to split attention head parameters and split per attention head parameters and workload across GPUs, and doesn't require any immediate communication to complete the self-attention. So as you can see, we did that. We completed the self-attention without any intermediate communication between the devices because the heads are completely independent. The subsequent gem from the output linear layer after self-attention is parallelized along its rows and takes the output of the parallel attention layer directly without requiring direct communication between the GPUs. So this is what I'm showing here. This is the output matrix, right? It would look like this, right? But we parallelize across rows, and so we have one chunk of rows going to be working with this first attention head, one chunk of rows operating with the second attention head, and so on. We perform this mat mul, and we get this shape, number of rows in the left operand, number of columns in the right operand. We get this output, and then finally at the end, we're now at the end of the multi-head attention layer. So we can now do our all reduce of these partial results, right? And oops, I misspelled output. And now we can send the full complete outputs through dropout, right? And so let's cross-reference that with their diagram that doesn't show the shardings or anything, but is like the source of truth here. So yeah, X is replicated. X goes into the Q, K, and V projections. Then the K and V projections are map mul, softmax. Okay, I didn't include dropout in my diagram here, but there's an intermediate dropout here, and then the output of the attention scores are map mul with V to get this like updated kind of like adjusting its location in vector space essentially based on the weighted attention scores. And we have those outputs of each of the attention heads, right? Because these are where the attention heads are kind of dividing the hidden dimension, the model hidden dimension, and kind of like attending to them or looking at them, doing the computation separately, so we can do them in parallel and kind of learn different representations for each parts of the model dimension. Um, Anyways, we pass these in now, and now we're in our linear layer that comes after the self-attention. Those go to our, they call it B here. It's just the matrix partitioned row-wise, and that we can compute. We get Z. That's our equivalent to our output 1 and output 2 here. And then now, finally, G. G is an all reduced in the forward pass, identity in the backward pass. So G, we all reduce and then go through dropout as I've shown here. Okay, so that's their version of the diagram. Cool. Let's keep reading the paper. This approach for both the MLP and self-attention layer fuses two groups of gems, eliminates a synchronization point in between, and results in better scaling. This enables us to perform gems in a simple transformer layer using only two all reduces in the forward path and two in the backward path. So as you can see, in the backward path, when we compute our loss for propagating the gradient back to these layers, G. So I'm looking at the MLP. G was an all reduced in the forward pass, but it's an identity in the backward pass, meaning it's going to be that gradient, the upstream gradient, is going to be replicated to both devices. They'll continue their local backprop according to there, and then F was a F was a identity or replication in the forward pass, so it becomes a all reduced in the backward pass. These two partial gradients that we've computed through these two paths across two devices of this partition computation we've done need to now be reduced to now propagate the full gradient back through X. So that's kind of what they're talking about there. So that's kind of the key takeaway here is that for MLP and self-attention, aka the components of a transformer decoder block, they require two all reduces in the forward and two all reduces in the backward. And this means that you multiply, for the forward pass, it's going to be 2 times your number of transformer decoder layers. It's going to be your number of all reduces just for the decoder layers, because we haven't gone to the input and output embeddings yet, and the loss, the cross entropy loss. But that's how many all reduces are going to be needed in your model for the forward, and then 2 for the backward. So we're talking about 4 total, 4 times the number of transformer blocks. And this is the number of all reduces for a forward and backward pass. All right, let's move on. Now we're going to talk about the input and output embeddings. This gets a little tricky, especially the output embedding, but we're going to go through it step by step. So a transformer language model has an output embedding with the dimensions of hidden size times vocabulary size. Okay. Since the vocabulary, so this is where we project from our hidden dimension back to the vocabulary dimension so we can compute our logits and cross entropy loss. Since the vocabulary size is on the order of tens of thousands of tokens from our language models, so it's like over 50,000, it is beneficial to parallelize the output embedding gem. However, in transformer language models, the output embedding layer shares weights with the input embedding, requiring modifications to both. Because these input and output matrices are essentially transposed of each other, right? The input projects from the vocabulary dimension to the hidden dimension, the embedding dimension. So from input, we go from vocabulary dimension to embedding dimension. Then in the output, we go from embedding dimension to vocabulary dimension. We parallelize the input embedding of the weight matrix, which is weight matrix E, which has H columns and V rows. So that's H, this hidden dimension, and V, this vocabulary dimension. I think they use H for hidden here. I think they basically mean the embedding dimension. But yeah, so they partition it column-wise along the vocabulary dimension. So this was really confusing to me at first. So it says, since each partition now only contains a portion of the embedding table, this is supposed to be highlighted, and all reduce is required after the input embedding. So I was confused by this because I was like, okay, if we're partitioning along the vocabulary dimension, that means that each device only has a subset of the vocabulary. So when tokens from the input sequence arrive into the input embedding on that device, we won't be able to look up all the embeddings for them because a token on device 0 might have its embedding live on device 1 because we've partitioned across the vocabulary dimension. So that just seems like a weird way to do it, especially because they say an all reduce is required after the input embedding, but it seems like what would be required is an all gather because we can only look up a subset of the embeddings, and then it would seem like we need to collect them. But um, I managed to figure this out by diagramming it out and researching online, and it's just, I found it kind of frustrating. It's just so sparse, the detail here. It's like one sentence, and they move on to talking about the output embedding, which is even more confusing. So let's go, and we'll save you all some time and show you what I figured out about the input embedding. So this is what's happening. So they say the input embedding matrix is partitioned across the vocabulary dimension, right? So let's draw it out. We have the input embedding with the embedding dimension being the rows and the vocabulary dimension being the columns, and we partition down the columns across the vocabulary dimension. So green is the first device, blue is the second device, right? And now what's going to happen is, and I should give credit to how I figured this out. No, not here. I think it was it Y, row wise? Here it is. There's this GitHub issue on Torch Titan, which is like a reference implementation of different LLMs with the associated training code and different styles of parallelism supported in PyTorch. And somebody's asking this exact same question. They're asking why. Well, I won't repeat it. They're asking the same thing. Basically, why are we sharding along the vocabulary dimension? It's like it makes it less clear. It's kind of confusing. And Tianyu here answers with these details. So basically, says they should both work correctly. Partitioning along the hidden dimension or the vocabulary dimension, but the difference is basically just in the communication. And so what he says is with row-wise, which is in this case partitioning along the vocabulary dimension, right? Because this is a little different than the Megatron paper the way, but just to show you that is the case. They're saying row-wise splits on the token dimension, leading to confusion on how the different shards handle tokens that are not present within their shard. So that's exactly what we're talking about with the token embeddings. Okay, so he's saying with row-wise, after the layer embeddings would be stored in a mask partial, which I'll open up here, placement, mask partial placement, and requires a reduced scatter to be sharded on the sequence dimension in sequence parallel, or all reduce if vanilla tensor parallel. Okay, so let's ignore this part for now about sequence parallel in the subsequent layer. We'll actually cover that next week in our next paper, but let's focus on all reduce if vanilla tensor parallel, because this aligns with what our paper says. It will require an all reduce after the input embedding. So if we look at the implementation here, and this is what the Megatron authors are doing as well, I believe, since they're using all reduce, a mask partial is a partial mask placement device for a row-wise sharded embedding operation where we need to mask and adjust the indices to the local embedding shard. Embedding masking is a special type of partial placement. So if we look at what this means, basically it's saying we need to adjust the indices in order to match what is actually available on this local shard, right? Because on our local shard might be indices like 100 through 150, but our tensor to index into it, we need to index 0, right? Index 1. We're not going directly to 150; it'll be out of bounds. So we need to adjust the indices and mask out any tokens that are trying to they would access an index which is out of bounds of the local shard, right, that exists on another device. So how they do that here is they find the offset associated with this local shard and subtract, and then they set to so that now that we can are indexed by 0 again, right? And then using our mask, which we calculate here, for any elements of the tensor which are out of bounds of this particular local shard, it sets it to 0, right? So it uses a mask to rather than provide an embedding for that token, if that token is trying to access an index which is out of bounds for this local shard, it sets it to 0, right? So what that will look like in the diagram is, say here comes some token embeddings, right? if we have 0, 3, 1, 2, 0 is a token, 3 is a token, 1 is a token, 2 is a token, then we replicate just like in the previous layers. I just want to be clear. When I say replicate, I don't think it's like literally only on one device and being replicated. It just is like easier to think about that way. They already exist on both devices. But now for this is on device 1 and this is on device 2. 0 does exist on device 1, right? So we get the right here we get the E0 embedding. 3 does not exist on device 1. That index is out of bounds of the local range of indexes available on shard 1, so or shard 0 in this case, I guess. So then we get a 0, right? And then same thing for index 1 here. We do the same process. E1, the index embedding at index 1 does exist, so we get it. And then 2, index 2 is out of bounds, so we get a 0. And we go through the same process with the second partition, but now, when we look up 0, it's not there, so we get a 0. When we look up 3, it is there, so we get E3 and so on. So now what we have is these two partial sets of embeddings on the different devices. And they are complete embeddings, but they're just missing certain tokens that were not available in their local lookup table eventually. So then now this is why we do an all reduce, right? Because now we can do an all reduce, and when we do a sum, between E0 and then 0, this will broadcast across the vector, and nothing will happen. Essentially, we get E0, 0 will broadcast with E3, and we get 0, we get E3 and so on. So now on each device we have a full set of embeddings for all of our input tokens in the sequence. And the advantage of this is that the vocabulary dimension is very huge, 50K plus. So, basically we managed to look up and get a set of embeddings for, get the embeddings for all of our tokens without having to have the entire materialized input embedding table on a single device. We could partition it across this huge dimension here, making that partitioning more impactful. And so we only have a partial embedding table on each device, but we can just check the indices basically, set the missing ones to 0, and then all reduce, and that way we do a little, we do expend some, the trade-off here is we have to do an all reduce, which would not have to occur if we had a full embedding table, but the trade-off is favorable because this huge embedding matrix with the 50K plus vocab dimension has been sharded across n number of devices. So, and the whole goal of this paper is trying to reduce the memory pressure, right? Allow scaling larger models. So that's how the input embedding works. So now, and it's crazy. All that is just from they just have this like one sentence. So yeah, I believe that's the way it works though. So now let's move to the output embedding. So now we'll go through all the transformer layers and we discuss the attention, the MLP, and so on. So now we get to the output, right? And we need to project from the embedding dimension to the vocabulary dimension and perform cross-entropy loss. So for the output embedding, one approach is to perform the parallel gem, which is going to be X, our input activations, by E1 and E2. These are where E is our embedding matrix. To obtain the logits, add an all gather Y to all gather because we are partitioning across the vocabulary dimension, and send the results to the cross entropy loss. So what this would look like, what they're saying here is that this, if you partition across the vocabulary dimension, you do this, you'll get the number of rows in X by the number of columns in E1, and the number of columns in E1, if you're projecting to the vocabulary dimension, that's your output dimension. So you will have an output matrix that only has partial logits, meaning a subset of scores. A score is for a subset of the possible tokens of the vocabulary. You'll have the same thing on another instance of that on the second device. So now the question is, how do we need to, for softmax, which is part of cross entropy, we need to be able to perform softmax across the entire set of logits, right? For one given prediction. So that means, the most straightforward way to do this is just to all gather them, right? We all gather, now we have the full set of logits, then we can perform softmax row-wise and get our, our weighted predictions, basically, a probability distribution. However, so what they say is, however, for this case, the all gather will communicate B times S times V elements. B is the batch size, S is the sequence length, and B is the vocabulary dimension, which remember is huge. So say it's huge and the vocabulary size is large. So to reduce the communication size, we fuse the output of this gem with the parallel gem with the cross entropy loss, which reduces the dimension to B times S. Communicating scalar losses instead of logits is a huge reduction in communication that improves the efficiency of our model parallel approach. Okay, so this right here was probably the most confusing part to me. I had to go look at the Megatron code to figure out what it's doing. And what I'm about to show you is actually not exactly what the Megatron code is doing, because they're doing some extra stuff to for numerical stability, like subtracting the max logit from all the logits in order to prevent when we exponentiate. As part of our cross entropy loss formula, we're going to exponentiate the logits and then divide by the sum of all the exponentiated logits to get a probability distribution of our logits for our prediction, for each prediction, But they subtract the max logit to do basically prevent overflow that can occur in that, and they also have an alternative formulation of cross entropy. Just like it's mathematically equivalent. I'm not sure if it's more efficient, but anyways, this is what I've come up with that I believe is what they're trying to say in this paper. So if we just take it one step at a time, the goal here is that they're saying, and even the way they phrase this is extremely ambiguous. I think what they're saying is, because they say communicating scale. Let's take it one step at a time about what I think, and then what I'm going to show in the diagram. They say the first, it reduces the dimension from B times S times V to just B times S, right? That's one goal. And they don't even say, they just say we fuse the output, okay? It doesn't really provide a lot of detail on how this reduces the vocabulary dimension to 1, right? It just shrinks. It is gone now, basically. And then it also just says communicating scalar losses, but this is not a scalar loss. This is for every single batch for every single sequence. And you don't have a separate loss for every single sequence. I mean, I guess you could have a separate loss for each prediction, but you sum them in the cross entropy loss formula. So, and then you aren't communicating a scalar at that point. I think, so I'll show you, let's not get hung up here. I'll show you, it doesn't make more sense when we look at the diagram, and then we'll come back to this. So this is what I think the fused output embedding in C loss is doing. So we have our input activations, right? They come in, and now we need to, from the sequence dimension and the embedding dimension, right? So for each element in the sequence, we have some embedding for it, right? And it's gone through all of our layers. It's, updated its position in vector space based on the surrounding context of the other tokens and so on. It's ready now to go through the embedding, go project back down to the vocabulary dimension, get our logits, and do our prediction. So how we're going to do that? We are going to map mul by the output embedding matrix, right? This linear projection here that is of shape embedding dimension by vocab dimension. Because again, they say, the only example they give here, it's sharded along the vocab dimension column-wise. So we're going to do that. This is how I drew it out. I drew it out partitioned column-wise across the vocab dimension, right? So what will that leave us if we do that? Well, we will have two sets of partial logits, one on each device, if we're using two devices, right? The sequence dimension, and then for each element in the sequence, we will have a partial set of logits, which has scores for each of the possible tokens in our output vocabulary, up until the partitioning boundary. So some subset of the words in our vocabulary, we will have scores for them, right? And same thing for GPU1. It will have scores for some subset of the tokens in our output vocabulary now. So what is the shape of this? What is the shape of this now? On each GPU, we have a shape of batch times sequence times vocabulary divided by 2 on each GPU. Okay. Now, in order to compute cross-entropy loss, we need to do two things, right? Because it's saying we don't all gather, right? Because the obvious solution here is to all gather and then compute CE loss. So how do we do it without all gathering? So we need two things for CE loss. We need the softmax denominator. First, we need to compute softmax, right? And then we need, maybe this will just be a good reminder. Maybe I'll just write out the formula for us so I can reference it as I talk. So cross-entropy loss will be sum of P of x times log of Q of x. Oops, sorry, it's negative at the front. For all I. So we'll just, you can hopefully read my math notation here. Basically, Q of x, in this case, Q of x is our predicted probability for a given token, for token xi, and P of x is the true probability of token xi, right? So, okay, now we have our definitions. Let's take this down. So to get the probability Q of x, right, we're going to need Q of x equals softmax of logits, basically, okay? And the formula for softmax is e to the x of I. This math hopefully is not like insane, like hard to read for you guys, but and then over the sum of all of e to the e to the x sub j for all j. Right? So it's just basically you exponentiate your logits, and then you divide that by the sum of the exponentiated logits, right? So that gives you a probability distribution. So that's what we're going to do here. So for the two parts of the softmax is the tricky part because we need access to all the logits, right? And they're currently distributed across the devices. So how are we going to do this? The two components we need are the softmax denominator, which is the sum of all the exponentiated logits, and the softmax numerator, which is going to be actually the only softmax numerator that we need is for the token associated with the target value, right? The target token, the true token value, like the true the label, basically, right? We have a prediction and a label that we're going to compare against. And maybe if I can just make this a little bigger, even so. So basically, the only reason we need, here, I'll bring this down, actually. I'll bring this down, down here. So the only reason we need the logit associated with the target token is because this will be 0 for one hot encoded vector. Basically, there's only one token, right? There's only one true token, like our labels. So label will be 1 for true token and 0 for all others, right? So basically what this means is that P of xi will be 0 for all of the, so this will be all of I in vocabdim. So P of xi will be 0 for every possible token we could have predicted in the output vocabulary, except for the one it actually will be 1, right? So that means that, when we do the sum across all i's, it's going to be 0 times something, 0 times something, 0 times something. It's going to be all zeros, except for finally, for the real token, the real true label, it will be 1 times log of our probability that we predicted that token would have. Okay, so this simplifies then. So I'll say, so C loss simplifies to negative log of P of xi by log of Q of xi, where xi is the token associated with the token, like the, oh my god, my words are failing me right now. It's the label token. It's the target token. We'll use target token. Okay. Hopefully this makes sense. So now, since everything will just become 0 except for that one. Whoops. Hold on. Okay, I'm messing up my math here. It is not this. It will be 1 times CE loss. Sorry, I'm getting tired. So just 1 times log of our, I guess it would be negative, and then 1 times our log. Okay, so 1 is the probability of that true output token, and then log, this is the log probability of our predicted output, our prediction for that token, and negative, because that's the, we can't lose that from the start of the equation. So in order to compute this, we need the, remember this Q of x has a softmax. That's how we got the probability, is because it was part of a probability, x of I was part of the probability distribution. Q of xi is part of a probability distribution for all of Q of x, which is a softmax. So we need the softmax denominator, which we're going to get up here, and then we have the softmax. We also need the exponentiated logit, like the numerator of the softmax, which is the exponentiated logit associated with the target token. And I'll put in parentheses down here, used in softmax numerator for target token. Okay, hopefully that makes sense. It's kind of tricky to explain. So what does this actually look like? So first, let's do the global softmax denominator. So we have our partial logits on each device, right? First, we can compute the exponentiate sum is what they say, but it's the exponentiated sum. So we exponentiate all the values and sum them. This is the same operation we're doing in our softmax denominator here, right? I'll bring this back up now so that I can reference this as I talk. And so this is for the denominator. We do exp-sum on the logits, and so you can see here would be the exponentiating all these values and then summing them, and then here exponentiating all these values and summing. You get this. Same thing with the blue, right? So we have our exp-sums. Now this is of shape b by s, right? And this is important. Remember, in our paper, they're saying this reduces whatever they're talking about here. this fused cross-entropy loss reduces the dimension to b by s. So let's remember that. Okay. Now we computed the local exp-sum of the logits. Now this is key. I believe here we do an all reduce, and they're saying this is better. There's actually 2 all reduces in this, and there is in the Megatron implementation as well. So I think this is correct. But the first all reduce happens here to get the global exp-sum of the logits, meaning the global softmax denominator, right? This denominator here for the softmax. To get the global value, we perform a local reduction exp-sum, and then we do an all reduce, and now we have the global softmax denominator for each prediction, right? Now we have the global softmax denominator. Now we need the numerator, which is going to be the only one we need is the numerator for the target token, right? Which is the exponential of that logit for that target, like the exponential of our predicted score for that token, right? So how we do this is we look at our target labels, right? And this would be in the form of the indexes of the target tokens, right? So we have our target tokens, our target labels will say, they will not actually be like literally one hot encoded where like for each, element in the sequence dimension, we have 50,000 element vector with all zeros except for a 1 in the location of the true token. They will just provide, it'll just be an index, right? It'll say like the correct index in the vocabulary dimension for this prediction, the correct token was 4. Okay, the correct token for this example is 2. Okay, and so now what we can do is we can compare that token, or we compare that index with the range of indexes available in our partial logits on this device, and we can say, okay, 4 is out of range, so we actually can't get the exponential of the logit on this device because it doesn't exist on this device. So we just set it to 0. Okay, we mask it out. We mask it out where the shard does not have the logit for the target, right? However, on device 2, when it does when it checks that index 4, 4 does exist here, right? It's 0.3. So you can do the exponential 0.3, right? And you get this value. I think. I hope I did that math right. I've played around with this diagram so much that might be an outdated value, but hopefully that's right. And basically, it gets the point across though. So now we can go through and mask out the values whose logits, let me say this again. We get the exponential of the logit associated with the true token. Right? We see what our predicted score was for the real value, the real token, the real label. What was our predicted score? And at each element, if that logit, if that predicted score exists on this device, we exponentiate it and put it here. If not, we mask it out and just put it as 0, right? And so now we will have 2 sets of partial exponentiated logits for predicted logits, right? Now, okay, so now we have our numerators, right? Because this is, again, for this formula, right, we just need log of q of x. And how do we get log of q of xi? It's just the softmax probability for q of I, or sorry, for x of I, for which we need if we look at the formula for softmax right here, we need the exponential of that, like our prediction for that token, divided by the sum of all the exponentials of the tokens, right? So we have that. We have our sum from the all reduce here. That's the denominator. And now we have this, the exponentials of the logits that were predicted for the true values, right? Hopefully that makes sense. It's a mouthful. It's tricky to explain. So now let's move on. Okay, so those are the 2 components, but remember we're still sharded across 2 devices. So if we look here now, what we can do is we can use the global softmax denominator, which does exist on both devices because we've done an all reduce, right? And then, so the global softmax denominators are on both devices, but the exponential logit associated with the target token, right, the true token, what was our predicted score for that token? Those are still partitioned across the devices based on the vocabulary dimension, since we shard across the vocabulary dimension. So what we can do is we can compute the per prediction loss on each device, right? So we'll plug into the formula here. So let's look here. See how we have 0 for the first prediction for our sequence, first element in our sequence. What's the prediction for that? Well, on the first device, we had a 0. That score wasn't on that device, so we just do nothing. It just stays 0. However, we did have this 2, right? We did have that logit on device 0, so we compute the local loss for that prediction, which would be our formula, negative log of 2.0 divided by our softmax denominator, and that gives us this is supposed to be, sorry, these parentheses are not in the right place. It's supposed to be log of the full probability. There we go. Sorry about that. So we're going to take log of q of x, and q of x is computed using the the exponential of the predicted score for that token divided by the full sum of all the exponentials of the predicted tokens scores, right? And we do that in every place we can, or we just do it universally, but some will come to zero because there's a zero here, right? And so now what we have is a bunch of per token predictions, or rather per prediction losses, and then now we can sum these column-wise. So sum column-wise per prediction losses. So if you sum column-wise here, sum column-wise here, still staying on the same local device, you excuse me, you'll get this value and this value, and now you have scalar losses, local scalar cross-entropy losses that you can all reduce to get a global cross-entropy loss, which is consistent across devices and can be used to now to compute your gradients, perform backpropagation, and have the numerics be accurate. And so now let's reference our paper. Let's first summarize the amount of data sent over here, and then reference the paper to check our correctness. So the total data sent over the network was, in this first step, the batch dimension, which is just 1. And so this whole diagram is just for, I should say, for batch size equals 1. Right? I just want to clarify that because this would be impossible to draw with more than that. So for one batch size, it's going to be sequence dimension. So right here, this first I'll reduce sequence dimension by n, number of devices, right? So each sequence will have a x sum for the logents on each device. So it'll be sequence dimension by the batch dimension by sequence dimension by number of devices, right? This is total, right? It's B by S per GPU, and here I'm computing the total total amount of data sent over the whole network. So it'll be batch by sequence by number of devices. And then now our second all reduce at the end here is all reducing the scalar local cross-entropy losses, and that will just be 1 per device. So that is just n, the number of devices, right? So now let's cross-reference with our paper. They say for this case, the all gather, if you just all gather these logits directly without doing this kind of fancier technique, it would be B by S by V elements communicated over between devices, which is huge. So to reduce it, they fuse, and this reduces the dimension to B by S. So I think they don't say we all reduce on the B by S. This is why it's like a little confusing. But if you look in the Megatron-LM implementation, you can see here, look, here it is, vocabulary parallel cross entropy. This is in the fused. Oops, hold on, this is not the fused. Sorry, here it is. They first do an all reduce here. This is actually they're just getting the logits max. They're going to do for numerical stability, and then they're going to do another all reduce here, and they actually combine this value predicted logit sum combines the predicted logits sum x, and then also the denominator values for each row, basically. They do it all in one. They batch the tensors together and do all one big all reduce or something. It's kind of I don't quite fully understand how it maps to the paper. This code was only added a few months ago, and this is at the time of recording March 2025. Megatron came out in 2020, so it's been 5 years. I assume it's changed a little bit, is my best guess. But anyways, just suffice to say, the only thing being reduced here, what I'm trying to say is that, and why I brought this up, is that they're not just reducing only one scalar value per GPU into the fused output embedding cross entropy loss. There's more moving around than that. And what I think is moving around is I think they're doing the B by S. They're moving around B by S elements, and then they say communicating scalar losses. I believe they're doing that as well and reducing, like I did in my diagram here. This is my best guess as to what's happening from reading the paper and cross-referencing with the code, which has now been updated and whatnot, but gives you an idea of just, validates certain assumptions or certain ideas that like it doesn't seem possible. I don't know. I might be wrong, and I would love to have my either my understanding confirmed or corrected if there is a way to only communicate scalar losses at the end of this without doing this all reduce in the middle here. But yeah, this is my current understanding, and so that's how I believe the fused output projection slash with cost entropy loss works. Okay, that was a complicated one. Hope that made sense to everybody. Finally, we're just gonna wrap this up now. So they just now state, much of their approach is basically aimed at reducing communication, keeping GPUs compute bound. They actually make sure to call out that, for layers like, because we only talked about the self-attention, the MLP or FFN, and then the input and output embeddings in the cross entropy loss. I did not talk about dropout or layer norm and how to make those more efficient. So they don't do any kind of partitioning or any kind of special techniques on there, really. They actually just duplicate the computation, have the layer norm be applied just, individually on each GPU without kind of. So I'll just read what they say. They say, rather than having one GPU compute part of the dropout, layer normalization, or residual connections and broadcast the results to other GPUs, we usually duplicate the computation across GPUs. Specifically, maintain duplicate copies of layer normalization parameters on each GPU, and take the output of the model parallel region and run dropout and residual connection on these tensors before feeding them as input to the next model parallel regions. To optimize the model, we allow each model parallel worker to optimize its own set of parameters. Since all values are either local to or duplicated on a GPU, there's no need for communicating updated parameter values in this formulation. So this kind of leads us to our paper for next week, which is this one, which actually introduces, it kind of builds on this, and they take note of this and note that, we have our tensor parallel being used on our self-attention and, the linear output of self-attention here, and then also tensor parallel being used in our MLP here with our two linears separated by a nonlinearity. However, all these other layers, layer norm, dropout, etc., they see opportunities for efficiency improvements there. So what they note is, and maybe this is a spoiler for next week, but they note that layer norm, is normalizing along the final dimension of the quote unquote feature dimension or the hidden dimension in this case, or like the embedding dimension of the tokens, and there's no dependency between the tokens in the sequence. There's no computation or communication between them. It is applied independently. So they actually partition along the sequence dimension. And yeah, so I won't get ahead of myself here. We'll talk about this more next week. But this conclusion to our paper here kind of just naturally leads into kind of the next innovations that occurred after this. So we'll talk about that more next week. I'm not going to go into the rest of this paper in much detail. They just talk about their training setup, hyperparameters, the experiments they ran, and showed the scalability, 76% of perfect linear scaling. Did some experiments with different kinds of models to kind of show it generalizes, and then they conclude. I really wanted to spend the time to go through the actual technique and diagram it out, understand the math, understand the communication, and when communication is required and when communication actually wouldn't work and would not be equivalent to the non-partitioned version of the computation, and just kind of deeply understand everything that is lurking underneath these concise sentences here. So yeah, I hope everybody got a lot out of this. I certainly did, and I'll go ahead and end the recording now.